Hello everyone, my name is Yuan Chen from Zhejiang University. Today I'm going to present our paper SGXLock towards efficiently establishing mutual distrust between host application and enclave for SGX. This is a joint work with Florida State University and City University of Hong Kong. As we know, SGX is a popular TE solution that has been used in many scenarios to protect sensitive code or data, such as blockchain, finance, and healthcare. With SGX, an application would be divided into two components, the enclave and the host application. The enclave is used to protect the sensitive code or data. The enclave is isolated from the rest of the system, including the operating system and hypervisor. The host application is where the main program logic resides and acts as a proxy for the enclave to interact with the outside. In the design of SGX, it assumes that the enclave is trusted while the host application is untrusted. However, in reality, the enclave and the host application are mutually untrusted, such as third-party enclaves with flaw, which means the assumption of SGX is problematic. Then, we found that the problematic assumption of SGX introduces the Enclave-Host Asymmetry issue. The Enclave-Host Asymmetry issue consists of two components, the control flow asymmetry and the data access asymmetry. For the control flow asymmetry, it means that the enclave can jump to arbitrary locations of the host application, while the host application can only get into the enclave with a predefined entry. For the data access asymmetry, it means that the enclave can access the host application's memory region directly, while the host application cannot access the enclave's memory region because the enclave is hardware isolated by SGX. In this work, we present SGXLock. The goal of SGXLock is to eliminate the enclave host asymmetry and establish mutual distrust between the enclave and the host application. To eliminate the control flow asymmetry, we leverage a single-step mode to confine the jump target of the enclave existing to the specific location. To eliminate the data access asymmetry, we leverage inter-memory protection key technique to confine the enclave can only access the limited host application's memory region. First, let's look at how control flow asymmetry elimination works. When we read the Intel software developer manual, we found an interesting feature. It is that the single-step mode would regard the whole execution inside the enclave as a single instruction. That inspires us to consider that if we enable the single-step mode before getting into the enclave, then when the execution decides to exist in the enclave, a single-step exception would be triggered. Then that gives us a chance to check whether the jump target is valid. Here is the workflow. First, before entering the enclave, we enable the single-step mode, and then the CPU executes in the enclave. And when existing, a single-step exception is triggered. It's simple. Next, let's look at the data access asymmetry elimination. It is based on Intel MPK technique. Firstly, in the initialization stage, first we would allocate different MPK keys for the enclave and the host application respectively, E for the enclave and H for the host application. And then we allocate a parameter buffer, which is part of the host application's memory region, and we assign it with the enclave's MPK key E. And at runtime, when the execution is in the host application, the access permission of the CPU is set to E and H. Notice that even though the CPU has access permission to E, it cannot access the enclave's memory region, because the enclave is hardware isolated. And then before getting into the enclave, first we would copy the input to the parameter buffer. And then we would remove H from the CPU's access permission set, and then get into the enclave. With such an operation, the execution inside the enclave will not be allowed to access the host application's private memory region. And then after getting into the enclave would load the input, consumes it, and generate the output, and then transfer the output to the parameter buffer. And then exists the enclave. After existing the enclave, first we would extend the CPU's access permission set to E and H, and then we would copy the output data from the parameter buffer to the host application's private memory region. However, there are still two challenges to solve so that our enforcement cannot be bypassed. The first challenge is to block PKI register update inside the enclave. The PKI register represents the CPU's current access permission to MPK keys. The second challenge is to prevent the enclave from manipulating the host's application's stack pointer. Here is our solution of challenges. For challenge 1, there are two instructions that can be used to update the PKI register inside the enclave: XRestore instruction and WRPKI instruction. For XRestore instruction, it regards the PKI register as part of the processor's extended state and restore it with data from memory. Our solution to it is kind of easy. Just disable the bit 9 of the enclave's SFRM field is okay. WRPKI instruction is used to update the PKI register directly. Our solution to this is to leverage binary inspection technique to avoid the occurrence of WRPKI instruction inside the enclave. Our binary inspection technique consists of two parts: static inspection and dynamic inspection. Static inspection targets for plain enclave code. It works at the enclave creation outside the enclave. Dynamic inspection targets for dynamic loaded or generated enclave code. It works at enclave runtime, and it is triggered by write XOR execute permission violation. And it relies on a small piece of embedded code inside the enclave to finish the inspection process. For the second challenge, we perform post-stack integrity check based on a secret key to solve it. Our prototype is implemented based on Intel SGX SDK for Linux, and our evaluation is performed on a platform that supports both SGX and MPK. For macro benchmarks, we evaluate row equal or equal latency. Row means there is no workload for the equal or equal. For example, for row equal, it means we just get into the enclave and then get out of the enclave immediately. We can see that the SGXLock introduces relatively high latency overhead for the host-enclave interaction. But we need to notice that there is no overhead introduced for the execution inside the enclave or outside the enclave. For macro benchmarks, we choose 3 scenarios: machine learning inference service, database operation, and HTTP web server. We can see SGXLock is efficient in these 3 real-world scenarios, even with high frequency OCOS. Let's come to the conclusion and the takeaway. The first is that the blind trust of the host application to the enclave introduces the Enclave-Host Asymmetry. The second is that in this paper, we present SGXLock, a defense solution to confine an untrusted enclave's behavior. And lastly, our evaluation from real-world scenarios shows the efficiency of SGXLock. And that's all. Thank you for listening and any questions.